everyone, my name is Akriti and I'm an applied scientist at Microsoft. I worked on this project, engineering an intelligent essay scoring and feedback system, in my last semester at Northeastern University before I graduated in December 2020, and I'm very excited to present it before all of you today. I always like to start a presentation with acknowledgements since people are still paying attention, and the projects are never complete without the help and support of people in here. First and foremost, thanks to my co author Kelly for her work on the project as well as the manuscript. Special thanks to our amazing faculty members Chandra and Ian. This project would also not have been complete without all of the effort put in by my batchmates Chetna, Gabriel, Matthew, Nicholas, Philip, Rupa, and Shuchang. Recent advancements in machine learning, the availability of open source tools and libraries, and the decreasing costs of hosting applications on the cloud have created opportunities for small and big businesses alike. However, the engineering challenges surrounding these ML based applications prove to be significant, especially when a transition from prototype to production occurs. This paper describes our work in engineering a prototype intelligent business system with the aim to make evolution and transition to production as frictionless as possible. We describe our experience in translating a complex business requirement from a client into an initial version of a cloud based ML application. Our client is a small business that allows customers to send in recruitment related essays, which are then graded by the employees on a number of dimensions based on a predetermined rubric. The score is taken as a proxy for the quality and completeness of the knowledge and sentiments expressed in the essay. In addition, textual feedback is given for each of the dimensions, and this contains both constructive comments when more work is needed as well as the appreciation for a point that is well written. Our client came to us with a set of primary requirements, and we wanted to build an extensible, modifiable, scalable, cloud based framework for the application, developing initial ML models for the various dimensions of essay scoring deployed within the framework. For the model deployment, we were provided with a label dataset consisting of around 1,000 essays from the business's existing customers. And from an ML perspective, 1,000 documents is a small dataset for training purposes. It was therefore a requirement for our system to evolve downstream as the larger volume of training data became available. This means that the models should be capable of either online training or provide a straightforward mechanism to update the models when subsequent offline training had been performed. The first step was obviously to normalize the client provided textual inputs for the downstream ML algorithms. The output of this pre-processing is then transformed into a custom data type and then passed on to the next phase of processing. A copy of the normalized essay is passed on to multiple decoupled ML experts, which operate in parallel to process a particular essay dimension. This architecture exploits the fact that the dimensions are orthogonal and require a specific machine learning model each to provide the necessary automation. It also supports modifiability in that the models can be independently updated and new models can be added if new dimensions are added to the business problem. Each model stores its outputs, namely a score and a textual feedback, in a master object abstraction. Finally, once all the scores and feedback are approved, the application generates a PDF with the details about the customer, scores, feedback that can be sent as a report to the customer. Algorithmically, we decided to address the ML problem as a classification problem. Even though the amount of training data was small, for some dimensions, we first tried using two popular word embeddings, BERT and ELMO, and these were used with simple neural network classifiers to understand the difference in evaluation of the models. For other dimensions, we tried word-to-vec representation as well as different variants of BERT. In addition, we developed and evaluated classifiers for all the dimensions based on standard machine learning methods, including multinomial Bayes support vector machines. In these systems, we used a much simpler bag of words representation. We also built the system so that the basic architecture could be executed in two modes. Local invocation from a command line supported testing and evaluation purposes, and this mode also supported the development team and was especially important for the model refinement. And the architecture could also be deployed on a cloud platform to facilitate the operations and integrate with the data management system that we built. The cloud architecture that we built to run the application is hosted on AWS. It was designed to accommodate the size and processing time of the machine learning models used. The final cloud architecture is contained in a single virtual private cloud and consists of an elastic load balancer, AWS Lambda, an elastic file system, and EC2 instances that execute the models. The system is invoked by sending the input essay as a web request, which triggers the application code housed in an AWS Lambda function. And then the application dependencies, which are stored in the EC2 instance, are then accessed through an EFS access point, and the models which reside on a collection of EC2 instances are invoked. Of course, there were a lot of challenges. The models we deployed are highly heterogeneous, built by different people on different operating systems with different dependencies, and bringing them all together during the deployment exposed us to the challenge of package versioning. This is an ongoing problem in the industry, especially because of the lack of complex logging mechanisms for AI systems. We also had issues with scalability. Developing large sized models was relatively straightforward on our powerful development machines. We soon discovered deploying the same models on the cloud incurred high hosting costs to ensure adequate performance. Testing of machine learning based systems is challenging. Traditional testing techniques aim to increase the coverage towards the exploration of diverse software states. However, the understanding about the errors found in machine learning models is currently limited, thus leading to arbitrary bug detection and repair approaches. Additionally, the interpretation of the model results is not always clear or straightforward. This is especially true when working with text data and using contextual word embeddings to vectorize the data. In addition, the long execution times of our models caused another architecture modification, and we avoided the timeout issues by replacing the API gateways with an application load balancer, which will help with the performance in the long term. In our experience from this project, the transition from open ended client requirements to an initial implementation of an intelligent system is not straightforward to achieve. In our case, the client wanted automation of the scoring of customer submitted essays. To achieve this aim, we designed a modular software architecture that contains components for deploying and executing machine learning models. The individual machine learning model results are then combined together to get the final result. In this way, it is much easier to remove any unwanted models, change and evolve the algorithms of the existing models, as well as add new criteria without affecting how the application runs. The development of this application is still in its infancy, and the initial system we have built is being used as the basis for further development of the application capabilities and adding more usability features. Considerable further model validation enhancement is needed before all the dimensions of essay scoring can be adequately automated. However, we hope that a first operational version can add business value and can be deployed later in 2021. Thank you all so much for your time, and I look forward to any questions that you may have.
Live. Okay. All right, so we're live. Thank you for an interesting talk here, Akriti. So I see there's one question in the chat for you. So it's from Jane, and she's asking, you had multiple models, each of which performed a different task. Was your SE experience the same for each model, or did you observe any major differences across the different aspects models of scoring solution?
That's a very good question, and I think the point answer is that yes, there was a difference, a software engineering experience for every model, but I think that was kind of expected. So for smaller models like the back-of-word models, which didn't require a lot of computing power and could be easily integrated into the entire system, it was obviously much easier to use the module that we had built to connect it to the software engineering side of things. However, when I also mentioned in the workshop, in the paper, that when we were trying to use heavier models like Elmo and BERT, which required more complex calculations or heavier models, it was actually much more difficult to integrate it, whether it was because of the space limitations or just the fact that there's a lot more parameters to be taken care of when we were trying to integrate those models.
Okay, so we have about a minute and a half left, and I'll go ahead and ask you a question, Akriti. So you have lots of models, and I'm also assuming, given the limited data set, you said, as more data becomes available, the model needs to be retrained and things like that. Mm-hmm. How do you keep tabs on model drifting and the need to retrain them? Is there anything you do to evolve these models with time?
So that's a very good question. So we actually didn't even get to that part when we were at the end of this project. So like I mentioned, this was a short-term commitment with the client that we had. And we realized very early on that since we don't have enough data right now, we might not even be able to give him models that work properly. So as of now, the system was extremely rule-based. But when we handed over this project to the next team who was going to maintain it, we did end up mentioning and telling them that the model one need to be retrained such that they can even be used the first time. Because imagine having 1,000 essays and having a complicated machine learning model to be, getting the results from that. So our major focus for this project was actually just building the software engineering side of things and getting things ready for when we have enough data available for building better machine learning models.
Okay, great. We are out of time. And again, thank you very much for a great talk.
All right. Thank you so much for having me. Bye-bye.